Hello friends, welcome to my channel. This is Thermodynamics and Power Plant Isro question paper from 2006 to 2016 part 9. Question is, a system is undergoing a cycle that consists of three processes. During the first process, the work is 5 kJ and the heat is 23 kJ. In the second process, no work takes place and the heat interaction is minus 50 kJ. The third process is adiabatic. The work in the third process is, we have to find out the work in third process. I will do it in two processes, method 1 and method 2. First we will write the data given. During first process 1 to 2, W12 is 5 kJ, Q12 is 23 kJ. Second process 2 to 3, no work takes place, so W23 is 0 and the heat interaction Q23 is minus 50 kJ. Third process 3 to 1, third process is adiabatic. W3 to 1 we have to calculate and Q3 to 1 is 0. First method we will use here. For a cycle, del Q equal to del W. So 23 minus 50 plus 0 equal to 5 plus 0 plus W31. So W31 equal to 23 minus 50 minus 5. Minus 55 plus 23 is minus 32 kilojoule. So from option A is our answer. Then method 2. Here individually we'll do. We'll use this one, del Q equal to U plus del W. Change in internal energy plus watt. So in method 1 to 2, here 23 kilojoule heat and internal energy U2 minus U1 plus 5. So U2 minus U1 is 23 minus 5 is 18 kilojoule. Equation 1. Process 2-3. Heat transfer is minus 50. Then U3 minus U2, change in internal energy. Work done is 0. So U3 minus U2 equal to minus 50 kilojoule. Question 2. Then 3 to 1. Heat transfer, it's adiabatic process, so it's 0. Then U1 minus U3 plus W31. W31 we have to calculate. Here W31 is U3 minus U1. From equation and equation 2, we will get U3 and U1 relation. So from equation 1 we will subtract equation 2. U2 minus U1 is 18, then U3 No need to subtract. Just if we will add this one, we will get U2 cancel, then U3 minus U1 is minus 32 kilojoule. So put this value here. U3 minus U1 is minus 32 kilojoule. Same answer here also we will get. A is our answer. Velocity of sound in winter compared to summer will be velocity of sound in winter is less than velocity of sound in summer. So B is our answer. Gaseous nitrogen at 30 degrees Celsius is expanded through a converging nozzle from a total pressure of 0.5 megapascal to a back pressure chamber. If the back pressure is increased from 0.1 megapascal to 0.4 megapascal in steps of 0.02 megapascal, the trend mass flow rate through the nozzle is how much? We will draw the graph mass flow rate versus back pressure. M dot versus PB by PO. Back pressure and stagnation pressure ratio. Here it will remain constant for some time, then gradually decrease. Here it is maximum mass flow rate, its maximum, or its critical point, P star by PO. If we will start from here, 1, 2, 3, 4, then 5. It will remain constant till a point, then gradually decrease. C is our answer. Here P star is critical pressure, PO is stagnation pressure, and PB is back pressure. Critical to stagnation pressure ratio P star by PO for an expansion process is how much? Here already discussed in my previous video. T2 by T1 is P2 by P1 gamma minus by gamma. This one we will use here. P2 by P1 is T2 by T1 whole to the power gamma by gamma minus 1. Here for critical temperature and stagnation temperature, it's 2 by gamma plus 1. So P star by PO is T star by TO whole to the power gamma by gamma minus 1. So T star by TO, from here we will put 2 by gamma plus 1 whole to the power gamma by gamma minus 1. It's P star by PO. Critical pressure to stagnation pressure ratio. It's 2 by gamma plus 1 whole to the power gamma by gamma minus 1. From option here, D is our answer. Starting from same initial conditions, an ideal gas expands from volume V1 to V2 in three different ways. The work done by the gas in W1 if the process is purely isothermal, W2 if purely isobaric, W3 if purely adiabatic. Work done is the area under PV curve. P versus V. This is the initial point. This is constant pressure process. Same initial condition. Then here it is isothermal process. Then it's adiabatic process. Here n equal to 0, n is equal to 1 for isothermal process, and n equal to gamma for adiabatic process, and here n equal to infinity for constant volume process. PV to the power 1 equal to constant, PV to the power gamma equal to constant. Here W1 in this case, for isothermal it's W1, it's W1, and W2 in isobaric case, and W3 in adiabatic case. From this figure, area is maximum here, then here, then this one. So W2 is greater than W1 is greater than W3. From option A is our answer. An engine works on Carnot cycle between 27 degrees Celsius and 227 degrees Celsius. The efficiency of engine is how much? Carnot engine. Higher temperature and lower temperature. T maximum is 727 degrees Celsius. So in Kelvin it's 1000 Kelvin. T minimum is 227 degrees Celsius. So it's 500 Kelvin. Here heat supplied to the engine, heat rejected from the engine. Work done. It's clockwise cycle. Efficiency you have to calculate. It's T max minus Carnot efficiency by work done by heat supplied. T maximum. So 100 minus 1000 minus 500 divided by 1000. 500 by 1000. 0.5. So efficiency in percentage is 50%. From option A is our answer. A steam thermal power works on its Rankine cycle. This is the end of thermodynamics paper. Thank you friends.